Today's class, I'm going to explain electric discharge machining working principles, performance characteristics, advantages, disadvantages, and application. The main aim of this session is to familiarize the students with electric discharge machining. The main instructional objectives in this session is designed in such a way that the students can understand the working principle of electric discharge machining and identify what are the different process parameters and variables, etc. And after completion of this session, the students are able to understand the process characteristics and know the merits and demerits and applications of electric discharge machining. Electric discharge machining is a non-traditional machining process that uses electrical discharges to remove material from a workpiece. EDM is commonly used for machining complex shapes or hard materials that are challenging to machine using the conventional methods. EDM is a versatile machining process that finds applications in various industries, including aerospace, automotive tool and die manufacturing, and medical device production, etc. So what is the main setup we are using in electric discharge machining? You can see in this diagram. So that is the main EDM machining, the tank. Here they're providing this tank and this the workpiece, and this stirrer. It will mix the electrodes and powder particles in the dielectric liquid, and this is the tool electrode where these electrons are flowing and impinging on the workpiece, and there is a computer, that is a power supply to the computer, and here ZNC controller. Okay, so this current sensors, what current is the tool electrode is having, that continues its monitoring, accordingly it will supply the power. Okay, so this is the basic setup is used to machining the workpieces using the electric discharge machining. We'll see that main working principle of this EDM. The working principle of electric discharge machining is based on the phenomena of electrical discharge or spark erosion. Here is a step-by-step explanation of the working principle. Setup. A workpiece and an electrode, either a solid block or wire, are placed in a dielectric fluid bath. The dielectric fluid acts as an insulator and coolant during the process. Second, electric discharge generation. A voltage difference is applied between the workpiece and the electrode. When the voltage reaches a certain level, it ionizes the dielectric fluid, creating a conductive plasma channel. Spark formation. As the voltage increases further, a spark or electrical discharge is generated across the gap between the electrode and workpiece. The spark creates an intense heat and a localized plasma region. Next, material removal. The heat generated by the spark melts or vaporizes a small portion of the workpiece material in the spark's path. The dielectric fluid cools the plasma, solidifying the molten material and flushing away the debris. Next, spark erosion. The repeated formation and collapse of sparks result in controlled and localized erosion of the workpiece material. The erosion occurs in the form of tiny craters or pits on the workpiece surface. Next, the relative motion. To create desired shapes or cuts, the electrode and workpiece are moved relative to each other. In the case of ram shinker EDM, the electrode is lowered into the workpiece, while in wire EDM, the wire is fed through the workpiece, cutting it into the desired shape. Flushing and filtration. The dielectric fluid, which also acts as a coolant and flushing medium, continuously flows through the gap between the electrode and workpiece. It carries away the debris and maintains a consistent working environment. So these are the basic the steps we are following to machine the component using the electric discharge machining. What is the performance of EDM? EDM offers several advantages and has a specific performance characteristics that make it a valuable machining process in certain applications. Here are some key aspects of EDM performance. One is the precision. EDM is known for its high precision and accuracy. It can achieve intricate shapes and tight tolerances, often in the range of micrometers. The controlled electrical discharges allow for precise material removal without causing significant damage or deformation to the workpiece. Second, hard material machining. EDM is particularly effective for machining hard materials that are challenging to machine using conventional methods. It can work on materials with high hardness values such as hardened steels, titanium, carbides, and exotic alloys. The third one is complex shapes. The non-contact nature of EDM, where the electrode does not physically touch the workpiece during the machining, allows for machining complex and intricate shapes. So, no chemical forces. Since EDM is a non-contact process, there is no direct mechanical force applied to the workpiece. This makes it suitable for a delicate or fragile materials that may deform or distort under traditional machining process. Next, heat affected zone. So this heat affected zone generates heat during the spark erosion process, but the heat affected zone is relatively small and localized. So this minimizes the risk of thermal damage to the workpiece, such as changes in material properties or heat-induced stress. Surface finish. So EDM can achieve excellent surface finishes even on materials that are typically challenging to machine. The controlled electrical discharges vaporize or melt the material, leaving behind a smooth surface. However, the surface finish can be affected by factors such as the machining parameters and the electrode material. Material versatility. EDM can be applied to both conductive and non-conductive materials. While traditional EDM is suitable for conductive materials, non-conductive materials can be machined using advanced variations of EDM, such as the use of conductive fluids or powder mixed in the dry electric fluid. So next, the EDM, what are the main applications of EDM? Electric discharge machining finds applications in various industries where precision machining of complex shapes, hard materials, and fine details is required. Here are some common applications of EDM. One is mold and die making. So EDM is widely used in the mold and die making industry. It can create intricate cavities, contours, and fine detail in molds and dies for plastic injection molding, die casting, and other forming processes. So EDM allows for precise application of the desired shape, ensuring high quality and accurate parts production. Next, automotive industry. So in the automotive industry, EDM is used for manufacturing the precision parts like gears, shafts, engine components, and injection molds for plastic parts, etc. The ability to achieve tight tolerances, intricate shapes, and high surface finishes makes EDM valuable in automotive component production. Medical device manufacturing. EDM plays a crucial role in the production of medical devices also, including the surgical instruments, implants, and dental tools. It enables the machining of intricate geometries and ensures a precise fit and functionality of medical components. Electronics industry. So EDM is utilized in the electronics industry for manufacturing precision components like connectors, small molds, and tooling for circuit boards. Its ability to work with conductive and non-conductive materials makes it suitable for creating the intricate features in electronic devices. Tool and die manufacturing. So EDM is extensively used in tool and die manufacturing for cutting, shaping and forming tools, punches and dies. It allows for the creation of complex geometries and sharp edges required for precision cutting and forming processes. Jewelry and the watchmaking. The idiom is employed in the production of high-end jewelry and intricate watch components. It enables the creation of fine details, precise engravings, and complex shapes in precise metals and gemstones. Jewelry and that watchmaking you have seen, the prototyping and rapid tooling. So EDM is often used in the prototyping stage of product development, allowing for quick and accurate production of prototype parts. It is also used for rapid tooling, where temporary or short-term molds and dies are created using the EDM to expedite the production processes. That aerospace industry also they're having the lot of scope to perform using this EDM. It's employed in aerospace manufacturing for machining complex components like turbine blades, engine parts, fuel injection nozzles, and various critical components made of exotic alloys or heat-resistant materials. Its ability to work on hard and heat-treated materials make it suitable for the aerospace applications also. Next, we'll see what are the merits of EDM process. So the main the advantages of this using the EDM process is the precision. The EDM is known for its exceptional precision and accuracy. It can achieve tight tolerances and produce the complex shapes with high repeatability. This precision is vital in industries where intricate details and fine features are required, such as aerospace, medical device manufacturing, and mold making. Next, machining of hard materials. One of the significant advantages of EDM is its ability to machine hard materials effectively. EDM can cut through and shape materials with high hardness values, including hardened steels, titanium, carbides, and exotic alloys. This capability is particularly valuable in industries where hard materials are commonly used, such as aerospace and tooling. Complex geometries. EDM excels in machining complex geometries that are challenging to produce with traditional machining methods. It can create intricate cavities, sharp corners, narrow slots, and fine details with ease. This makes it highly suitable for industries such as mold making, aerospace, and electronics, where complex shapes are often required. No mechanical stresses. Since EDM is a non-contact machining process, there is no direct mechanical force applied to the workpiece. This eliminates the risk of distortion, wrapping, or residual stresses that can occur with the traditional machining methods. It is particularly advantageous for delicate or fragile materials as well as for parts with these walls or intricate designs. Surface finish. So EDM can achieve excellent surface finish even on materials that are typically challenging to machine. The controlled electrical discharges remove material in a controlled manner, resulting in fine finishes with appropriate machining parameters and electrode materials. EDM can produce surfaces with low roughness and high quality. Minimal tool wear. Since EDM does not involve direct physical contact between the tool and workpiece, tool wear is minimum compared to the traditional machining process. This reduces the need for frequent tool changes and improving the productivity and reducing the cost in the long run. Non-conductive material machining. EDM can machine non-conductive materials such as ceramics, composites, and certain plastics using the specialized variations of the process. This expands its applicability to industries where non-conductive materials are common, including electronics and semiconductor manufacturing. Automation and unattended operation. EDM can be easily automated, allowing for unattended operation and increased productivity. Robotic systems can be integrated with EDM machines to handle repetitive tasks, enhancing efficiency and reducing the labor requirement. Versatility. So the versatility also one of the merit of this EDM process. It can work with a wide range of materials, including the both conductive and non-conductive materials. This versatility allows for the machining of various components across different industries. Additionally, EDM can be used on materials regardless of their hardness, making it a flexible solution for a diverse application. So, what are the disadvantages or demerits of EDM process? So, there is some the few disadvantages also there for using this EDM. First one is it's a slower machining speed. The EDM generally operates at slower machining speeds compared to traditional machining methods such as milling or turning or grinding operations. The repeated electrical discharges and material removal process require time, resulting in longer machining cycle times. This can be a disadvantage in high volume production environments where rapid material removal is required. Next, multiple passes. Achieving the desired shape or cut often requires multiple passes in EDM. So the material removal process occurs incrementally and complex shapes may require numerous passes from different directions. This can lead to longer machining times and increase the complexity in process plan. Limited material thickness. EDM has limitations when it comes to machining thick workpieces. As the depth of cut increases, the process becomes less efficient and the machining time significantly increases. So EDM is more suitable for machining thin to moderately thick workpieces. And for deeper cuts, alternative machining methods may be preferred. Electrode wear. The electrodes used in EDM experience wear during the machining process. The repeated electrical discharges cause gradual erosion and degradation of the electrode material. As a result, electrodes need to be periodically replaced or repaired, adding to the overall cost of the process. Cost of equipment and setup. The initial cost of EDM equipment can be higher compared to conventional machining equipment. EDM machines are complex and require specialized components and technologies. Additionally, the setup and operation for EDM can be time consuming and require some skill operators which can further increase the cost. Environmental considerations. EDM generates debris and waste materials in the form of metal particles and dielectric fluid contamination. Proper disposal and management of these waste materials are necessary to ensure environmental compliance. Additionally, dielectric fluid used in EDM may require filtration and maintenance to maintain optimal performance. Limited aspect ratio. The aspect ratio, which refers to the depth to diameter ratio of the machine features, can be limited in EDM. As the depth increases and the efficiency is decreases, and and the machining time becomes more significant. This can restrict the ability to create deep cavities or features with high aspect ratios. Limited surface integrity. Although EDM can achieve good surface finishes, the process can introduce small recast layers or heat-affected zones on the machine surface. These layers may have different properties than the bulk material and can affect surface quality or material characteristics in certain applications. I hope everyone understand how this electric discharge mission is working, the working principles, and what are the different parameters are involved, and what are the applications, merits, and demerits.